implicit differentiation. So let's just get it in shot there. Now it's quite a confusing start to a question. By writing theta equals inverse tan of 3x over 2 as 2 tan theta equals 3x, use implicit differentiation to show that d theta by dx is equal to k over 4 plus 9 x squared, where k is an integer. So what I'm looking to do is to use implicit differentiation on this thing here. So I'm going to differentiate both sides with respect to x because I want dx, but I'm differentiating theta with respect to x. So I'm doing d dx of 2 tan theta, and I'm differentiating with respect to x 3x. Okay, so that's what this notation here tells me. Now, if I differentiate the right-hand side first, that's nice and straightforward because 3x differentiated with respect to x is going to leave me with just the integer 3. This side, however, I'm differentiating with respect to x, but I'm differentiating something theta. So whatever I differentiate, I'm going to then have to write d theta by dx after that, which is what implicit differentiation is. So tan x, we know from our formula book, goes to sec squared x. So I'm going to, this differentiates to 2 sec squared theta, so sorry, not x, theta. And as I say, because we're differentiating with respect to x, but actually we're differentiating a function of theta, we need to multiply that by d theta by dx. So that's implicit differentiation. I know usually in Core 4 the implicit differentiation is using x and y, but in this case we've got a different variable theta. So then what do we do to get d theta by dx? Well, we rearrange this, so d theta by dx is equal to 3 over 2 sec squared theta. So not quite what we were hoping for. We've got this trig function in here. So how can we get rid of it? Well, let's think about what we've been told in the question. We've been told that 2 tan theta equals 3x squared. So immediately I'm thinking, well, I haven't got tan theta. I've got a sec squared, but I do know an identity. So I know that tan squared theta equals sec squared theta minus 1. Or however you've remembered that identity. So let's think about what we could do to the given thing here. We could square both sides, giving me 4 tan squared theta equals 3x all squared, which is the same as writing 9x squared. So I'll just get rid of that and write that as 9x squared. So that's kind of giving me a little bit of an in here, but obviously I've now got this in terms of tan, not in terms of sec. So now let's substitute in sec squared in. So we've got 4 lots of sec squared theta minus 1 equals 9x squared. Expand that bracket, and now let's just rearrange this to find out what sec squared is on its own, because if I can make sec squared the subject, I can substitute it in. So add the 4 and then divide by the other 4. So sec squared theta is 9x squared plus 4 all over 4. Okay, so I'm going to now substitute that sec squared into my original equation for dx by d theta. And in doing that, what I'm actually doing is I'm just trying to find something in the form that I've been given. So let's just think about making sure that we don't make any little errors here. We've got the 3 over 2, so that's this bit here. So this is the same as writing 3 over 2 times 1 over sec squared. So we've got 3 over 2 times 1 over 9x squared plus 4 over 4. Okay, so when you've got the two things divided here, so you've got 1 divided by 1 divided by 1, that's the same as putting the 4 up the top there. So I've actually got 3 over 2 times 4 over 9x squared plus 4. Okay, and that is very close to what we're being asked to do. I've just scrolled away from it. But what we're being asked for is we want 4 plus 9x squared, but we want just an integer on the top. So we can see that the top here is going to multiply to 12 over 2 times 9x squared plus 4. 12 divided by the 2 is going to cancel, leaving me 6 over 9x squared plus 4. And obviously the order of that does not matter. So that's what we're looking for with k equaling 6 from our question there. So that's how we would go about doing that first part of the question. Quite a lot of work for 3 marks, but in the end we can get k is equal to k is equal to 6. To part B then, I've just removed all the workings, but I have just put the answer to part A there because we're going to use that later on in the question. So the next bit says, hence solve the differential equation, given that x equals 0 and y is pi by 3, give your answer in the form some function of y equals some function of x. So this is the separation of variables question. We've got 9y, let's just grab a pen, 9y 4 plus 9x squared dy by dx equals cosec 3y. So let's get the y terms on one side, the x terms on the other. So divide by the 9y. And then from there, so that's going to be equal to cosec 3y over 9y. And then we want to have our dy over this side and our dx over this side. So we're going to, if we divide by dx, we end up with 4 plus 9x squared 1 over dx equals cosec 3y over 9y 1 over dy. Now when we're integrating, we want to have just dx, not 1 over dx. We have to just do y instead of 1 over dy. So I'm going to put both sides effectively to the power of minus 1. I'm going to flip everything. Okay, so in doing that, I get 4 plus 9x squared to the minus 1 dx equal to 9y over cosec 3y dy. And then I'm going to integrate both sides. Okay, so this is setting up what we have to do, and obviously now it's a case of doing it. So let's worry about we'll call this one the right hand side and this one the left hand side. Okay, so the left hand side is actually going to be found by sort of doing a standard result here. Now what we want to do is we want to integrate this. Okay, so another way of thinking about it is what differentiates to give this. Okay, and think about what we did in the first part. We differentiated tan to the minus 1 3x over 2 to give us what we've got up there, 6 over 9x squared plus 4. What we want is 4 plus 9x squared to the minus 1, or 1 over 4 plus 9x squared. So what am I going to do? Well, it's very similar. I just need to divide it by 6. So what differentiates to give this? It's 1/6 of what we did in the first bit. So this is something to spot. Okay, we spot it, brilliant, we've sorted the left hand side. If we don't spot it, we're going to have to do a lot more work. It's going to be really difficult to get the tan out of there actually, but that's what the question's asking us to do. So we wanted to spot that was our left hand side. So the left hand side integrates to 1/6 tan to the minus 1 of 3x over 2. Now let's worry about the right hand side. Now the right hand side is a bit more standard. Okay, I want to rewrite it though. So I want to integrate 9y multiplied. Now cosec is 1 over sine, but 1 over cosec is just sine 3y. So 1 over cosec is the same as 1 over sine, which is the same as sine. Okay, so I'm integrating that with respect to y. So let's give ourselves a load more room. because we're going to do integration by parts, I've got two different functions multiplied together. Here's our by parts formula, and if we remember the little acronym LATE, late, to remind ourselves what we want to choose u to be. So u is logarithms, algebra, trigonometry or exponential. So it's going to be an algebra term of 9y. So u is equal to 9y, and then dv by dx is going to be equal to sine 3y. So du by dx, differentiate this side, sorry, not dx, we're doing this with respect to y. So everywhere we see a dx, we're actually going to have a y. So let's just make sure the notation's right. So let's just quickly, I'm going to go through and change these as well actually. So this is only a semantics point. It doesn't really make much difference to what we're doing, but it's certainly worth being as mathematically accurate as I can. So that's going to go down to 9. Now we're going to integrate to find v. So integrating sine, we get minus cos, and we're integrating, so it's going to be minus a third cos 3y. Okay, so that's just how we go about integrating sine 3y. So if you need to sort of go back and revise that, then that's certainly worth doing. So then putting everything into our formulas. This is our formula we're using. So u times v, we've got 9y times minus a third cos 3y. So the 9 and the third are going to leave me with minus 3y cos 3y. So that's the first term. And then I'm going to subtract the integral of v, which is minus a third cos 3y, times by du by dy, which is 9. So again, that minus a third there is going to be multiplied by 9, giving me a 3 at the front there. I'm integrating now this term here, and this integral again is quite straightforward. We integrate minus cos, so that goes back to sine, but it's going to be a third sine. So I've got minus 3 times by a third sine 3y. Okay, so in all, that's the 3 there and the third there cancel each other out. So I'm left with minus 3y cos 3y, the first minus, the second minus, so plus sine 3y. Okay, so that's what the right hand side integrates to. So bring everything together. Again, I'm going to remove this workings and just go back up so we can see the question as well as what we did for the left hand side. So here we are then, we've now integrated both sides. So I've got the result from the first one, a third inverse tan 3x over 2 equals minus 3y cos 3y plus sine 3y. Now, because I've integrated, there's obviously a constant involved here as well. And that constant's really, really important, because once we're doing this trig, we want to find our final solution without the constant. So we're going to substitute in the limits that we've been given. Okay, so x is equal to 0 and y is equal to pi over 3. So I've got a sixth, the inverse tan of 3 times 0 over 2, so inverse tan of nothing, and that's going to be equal to minus 3 lots of pi over 3, which is times by cos of 3 lots of pi over 3, because y, remember, is equal to pi over 3, plus sine of 3 lots, again, shouldn't have had that bracket there, sorry, 3 lots of pi over 3, plus whatever this constant is. So at this stage we just need to do a little bit of work on our calculator. So inverse tan of 0, you might not need this one on a calculator, but because if you think about what the tan graph is doing, but at 0 that's just 0. So this whole term here is nothing. I've got minus 3 pi over 3, so that's going to be leaving me with minus pi. Cos of 3 pi by 3. The 3's are going to cancel, so I'm just going to do cos of pi, and I do just need to make sure my calculator is in radians for the rest of this. So cos of the value of pi is minus 1. So I've got minus pi times by minus 1 for this first term, And again, the 2 pi's cancel, so I'm now going to do sine of pi, and again, a standard result of 0 plus the c. Okay, so if we look at what we've got, I've got 0 equals minus pi times pi, so pi plus c. Okay, so then what we can see here is that for this expression, c is going to be equal to minus pi. So then putting all this together, we end up with our final solution of minus a sixth tan to the minus 1 3x over 2 equals minus 3y cos 3y plus sine 3y minus pi. Okay, and that is giving the answer in the form of some function of y equals some function of x. Now, if you do look at the mark scheme, you would have found that what they've done is they've just put c on the other side, and so they ended up with pi being positive there. But if you imagine adding pi to both sides, you would then get positive pi on this side. So if you're using the mark scheme as well as my video here, you might find that pi is not supposed to be a minus. However, it actually doesn't matter because it depends which side of the equal sign it goes. So another tough question there, another 7 marker. I think the toughest thing was spotting how this left-hand side was supposed to integrate, and obviously spotting that the right-hand side was integration by parts and doing that whole formula correctly.